And as I mentioned, there may be one or two questions which probably relate to metal additive in the exam. So let's go through this first. I don't worry too much about the exam. By the way, I don't think it will be too difficult. If you think it's difficult, I'd be worried. So let's just deal with a little bit about metal additive, really because there are a number of channels towards creating a metal part using additive. So we've really spoke mostly about 3D printing, metal printing. That's not the only approach. So let's just sort of have a look at that. So I've got a couple of examples where we're looking at incorporating metal into conventional additive manufacturing. So when I say conventional, I mean non-metal in this context, which is a little unfair because metal printing is also conventional these days, but I suppose most people still associate additive manufacturing with polymer printing. And then we'll talk about direct metal printers, okay, if you insist. Okay. All right, so yeah, and then no. Yes, I know. Yeah. Okay. Yeah. I know it works. I know the battery doesn't work. Okay, right. So direct metal systems, we'll talk a little bit about that as well. Okay. So incorporating metal into conventional additive manufacturing. There's a lot of methods, particularly around powder laser sintering technology, which involves sintering still of polymers, but then somehow arriving at a metal part. We've already spoken this morning about casting and producing casting patterns, so this is an alternative approach in there as well. And then maybe I'll talk a little bit about powder metallurgy systems, which is what we were just talking about just now. So for example, if you've got a powder sintering machine, SLS machine, there's nothing to stop you from mixing in metals into those polymers and then essentially creating a matrix composite where the polymer is the matrix. What would that give you? Well, it generally is aimed at trying to give you a little bit of improved wear resistance in particular. You know, polymers are quite soft and metals are significantly harder. So by rule of mixture, essentially what you can do is mix in the metals into the polymers and get an improvement in hardness. And that could be beneficial in certain applications. You might also get slight improvements in toughness. Compression modulus will improve. Tensile modulus usually gets worse. And you might get improvements in heat conduction and maybe even electrical conduction, or you could perhaps achieve RF shielding or some other effect using this kind of approach. So there's a company in Italy called WindForm that actually makes powders for laser sintering machines. So it's not just that you need to use the machine vendors' powder mixtures. The reason why this is an Italian company is not an accident that it's from Italy. As you know, probably that Italians are very famous for driving cars very quickly, and also motorcycles. And this is sort of built around the performance vehicle industry. So a lot of devices here are aimed at providing improved performance or adjustability on racing vehicles. So all the components that you see in the middle there, which are all made using WindForm materials, are either, they might be aerodynamic deflectors or aerofoils in various guises. If you know nowadays, when you, particularly in like Formula One and similar, formula racing cars, you do adjustments for a particular racetrack. So you might have a track which has got lots of curves. Therefore, you want lots of deflectors, so that allows you to go around corners very quickly. Others might have very long straights, and therefore you want more downforce and more aerodynamic performance, lower drag factors. So what they do now is they put a lot of component-based aerofoils on vehicles. So if you look at the front of an F1 car, and you look at the front aerofoil, it's not just a single aerofoil. You'll see lots of different segments in there, and they're all designed for different purposes, either to increase force, deflect air around the wheels or other features on the cars and stuff like that. Other things that might be wearable components, components that wear out, not components that you wear. These would be other things, that might last a race, and then you throw them away and replace them with another one. So there's for example, components that go around the drive chain of a motorcycle, for example, which would wear out. Stuff that goes on the foot pedals and things like that. And then also you see probably a number of components which are related to airflow. One of the great things about 3D printing, as we've already identified, is you can create very complex internal geometries on parts which are optimized for optimal airflow, and without too much additional weight. So ducting is quite common. So this is the kind of thing that you would use these kind of materials for, rather than going all the way to creating a metal part. In fact, in this case, one of the benefits in using metal polymer blends is in fact the weight reduction as well. And if you've got a vehicle and all you want to do is make that vehicle last for 1 hour as it goes around a racetrack, then it's a very optimal way of racing. I know that, I used to work with a Formula student. I think you probably know this competition, FSAE competition, which is normally held in the US, run by the SAE, and we used to sort of talk to the students and say, the best car is the one that drives around the circuit, or the optimal design rather is the one that drives around the circuit, gets over the finish line, and then falls to pieces, because it's performed its function and then no more. You don't need to. If it doesn't, then you've over-engineered it. It's not strictly true, but anyhow. A movement along from this with the polymer metal blends is, why not melt away the polymer from in this? And 3D Systems developed a process called laser form, which is a steel powder which is mixed in with polymer. You basically take out what they call a green part. You put it into a furnace to melt away the polymer, and then it also sinters the steel. So you then end up with a porous steel part, which is labeled a brown part, and then another process where you then put it into a furnace again, and then you infiltrate with a lower melting point material. In this case, it was normally bronze or brass, and that would then soak into the pores and make it a fully dense part, which is sort of like a machinable steel. It kind of worked very well, but it required you to have a furnace, and it was a bit messy, and expensive, so it never really was very popular. But there are still companies that are using this technology today, you know, they're able to make some quite nice parts from it, as you can see here. It takes a lot of skill and knowledge development to be able to get to a part as good as the one on the left there, but it is possible. And even so, the material properties, whilst they are definitely metal and quite therefore wear resistant, etc., again, because of rule of mixture and that you've got a relatively soft material in there, bronze or brass, it's not as good as a standard A6 steel, for example. So, you've got there's a bit of a limitation in application there as well. But it is a possible way to get through to a final metal part. And if you've invested in it, and then you can take advantage of it, it wouldn't be a recommended way now, because this kind of technology was developed before metal printing came on the market. So nobody buys these facilities today, not really. And even if they do, they buy it from it's more like the powder metallurgy type of machine, which I'll show you later. You guys are from India, therefore you know all about casting, because that's basically the home of a large portion of the world's casting is done in India. A lot of the knowledge on casting has come from India and was developed in India, so there's no point in me telling you how to cast things, because you all know much better than I do. So all I'm trying to say is, how do you get to casting patterns? A number of machines were developed which explicitly worked with wax and 3D printed wax. So there were machines from Solidscape. FDM machines from Stratasys were also had wax patterning. SLS in the early days worked with wax patterning as well. It's not a really nice material to print. It's very fragile. It's quite difficult to handle. It's patterning wax, so it is relatively high temperature for standard wax. It's not like your wax crayons and stuff like that. So it is reasonably good. It's obviously extremely brittle. But if you're familiar with wax casting, it's a great way to get into metal. Because if you're already a company, say for example, that have been doing, say, jewelry, for example, for many years using wax casting, then a 3D printer that feeds into that doesn't disrupt your standard operating methods. It's just a different way to get your pattern. So it's not a bad way to look at it. And in fact, making wax patterns is a messy and difficult process in itself. So if you can print those patterns and at the same time do things like print the tree or part of the tree that you're going to assemble the wax onto before you do the casting or the shell production, then that saves you some problems as well and makes it a little easier. So it's not a bad way to do it, and it's particularly suitable for the dental and the jewelry industries, because You know, the sizes of parts are probably quite important. The bigger the part that you're going to cast, the more difficult it would be to handle inside the process, more likely it is to break. So small parts are really good. And they use the droplet deposition method. So SolidScape, I don't know if they still exist anymore, in fact. There may be there's probably quite a lot of machines still around, but maybe they don't really exist anymore. There's probably something or something similar still around that does this. But it feeds very well into the precision casting community. So it would be very good for India, I think. So there's no point in me telling you about investment casting. You know all about that. One thing that is important to know is that there are other ways. For example, EOS have a machine that is called it's the EOS Int S for sand, and it's used for creating cores, because that's probably the more difficult part to make, so they're building the cores, not necessarily entire mold, using 3D printing, and then also a number of additional processes, materials have emerged. For example, ABS actually works very well as a casting pattern. It burns out quite well with very low ash content in a standard investment casting. The only thing that you tend to do is you need to maybe make the shell a little thicker so that it withstands some of the initial expansion during the burnout phase. So it's feasible to use a standard 3D printer. The stuff that very low cost using ABS works very well. I guess PLA should work as well, to be honest. Don't see why not. Maybe there's a little bit of an exothermic reaction in the slurry coating process. I don't know. Anyhow, obviously we've got lots of direct metal technologies. Terry Wohlers, when he gives his presentations and he shows the growth of the 3D printing industry, if he then shows the overall that growth compared to the metal printing industry, particularly, metal printing has grown dramatically over the last sort of 10 years. Huge increases in volume of sales and value of sales. So metal printing is by far the most successful part of additive manufacturing. And there are loads of companies. I noticed I've still got Phoenix in there. That doesn't exist anymore. Concept Laser is part of GE. So there's a lot of movement in this space as well. So just by example with DMLS, I mean, the results that you get with direct metal printing are sometimes, well, I think usually come out better than polymer printing, because the powder particle sizes are very small. So surface roughnesses and things like that, particularly in relation to polymer sintering, they're as good, or if not better, from a metal powder printer as they are from a polymer powder printer. A lot of that's due to the density of the material itself, because if you've got powder particles and they're high density, then they spread better, they pack better. You don't have to compress them. They're self-compressing. So the spaces between the metal powder particles, they tend to fill up, whereas with polymer, sometimes you still get voids and things. So I don't really need to go through much of this, to be honest. They're all very similar to each other. One thing that somebody was talking about, I don't know if these guys still exist. This was actually a company that is a competitor to Optimec. And I'm not sure the arrangement. I think maybe, in fact, they bought some of the rights from Optimec to use the lens process. The company Festo, it's owned by an Indian-born entrepreneur who's based in the U.S., I think in Michigan. I had some dealings with him a few years back, but I haven't seen much recently. The major benefit behind their machine, or as they said it, is that they wanted to make much bigger parts than the lens process is capable of. But maybe in the light of the competition from the wire arc systems and other DED technologies, maybe they're struggling. I don't know. I don't need to say much about this. And another one, just to complete the picture, really, is ultrasonic consolidation. This is kind of like uses an ultrasonic bonding method, yeah, it's got some benefits. You can do, as it seems, as it's shown here, curved sort of shell or panel type components. So you could have a substrate which is non-planar, which is therefore you'll get some nice strong parts here. Another thing is, because ultrasonic bonding is not a thermal process, you can embed sensors into this process without damaging the sensors through excessive heat. So it's got some benefits. I think it's always going to struggle because it's also got a lot of disadvantages. You know, the layup speed's not very good. You have to trim all of the tapes and things, so it's more of a hybrid process if you actually want to make 3D printed parts. Oops. So yeah, EBM. Just again to complete the picture. I mean, Arcam is now also part of GE. EBM, and there was a bit of a mention about using vacuum as opposed to shielding gases. There's some benefits there, obviously, in terms of the cost of the gases, if nothing else. Also, by using vacuum, you can reduce the impact of sputter during the melting stages and things like that. With EBM, using an electron beam, the absorptivity and the energy delivery is much higher, so you can get a much higher, or it's easier to generate heat into the system, which is good for high temperature alloys like Inconels and things. But again, nowadays, a lot of laser-based machines are also capable of providing those kinds of temperatures. So it's a good process. From people that I've spoken to, the major downside of EBM is surface texture is usually a little higher, a little rougher than the laser-based systems, but you know, I don't really see why that should necessarily be the case, and they can easily work on that and improve the technology accordingly. There's the only other thing that sort of coming to my mind is when you're doing laser-based powder bed melting, and you maybe, instead of using argon, you're using nitrogen, then you can get sort of nitriding effects on some materials, which can be a good thing, but can also be a bad thing. Mentioned about hybrid, Morisaki, basically just additive and subtractive, just again, another way to get to a part, bearing in mind that if you're making an internal surface, it's somewhat difficult to finish, and therefore machine finishing in build is maybe a way around this. whenever you've got NC machining, then you've got problems associated with path planning, tool selection, and other factors, chip formation, how much depth of cut, etc. should you be choosing. Very material specific and also material property specific. So it's not a straightforward process. It adds complexity. Might be good if you've got a part that you really know that you can do on this, and then you can do it in production, a little bit like the GE part. Lots of examples. What are they used for? We've seen loads of examples, so I don't need to worry about that. The only one that's not really I've spoken about very much is on the top right there, multiple material functionality, which is another benefit of using DED systems in particular. Fine. It's more of a feasibility thing rather than an actual thing. It's possible. Probably there are better ways, in fact, to make multiple material parts for the types of applications we currently look at. I mean plating methods and metal spray or other types of coating methods. If you really want to make a functional part which has a lot of variability in the material properties around it, there's a long way to go yet, because it's not an easy thing to do. Direct metals, good range of metals nowadays. The metals are useful metals, so titanium 6-4, a lot of steels, tool steel, stainless steels, cobalt chrome, there are now magnesium alloys, aluminium alloys, yeah, so there's an increasing number of them, still not very many, but the ones that are available are good materials, useful materials. So, so the applications are very, very good. A bit about gold. I just found this is my wife's ring. So just to give an idea of what you can do. So this would be quite difficult to make using conventional methods. There's a lot of crevices and issues in relation to this. So this was done by Cooks and Gold in the UK, designed by Lionel Dean of Future Factories. So just to give you an idea, my wife was quite pleased about it, and then she lost it. What was good about that? I had the design. I made another one. She hasn't lost that one. What else? Direct metal, process constraints. I think we've covered about that a lot. Size of part, resolution. Properties are actually pretty good. Few people, what we might use it for, great. Direct metal application. I've just noticed I haven't looked at binder printing on this. I don't know, I must have missed this off the end of my presentation. Just to mean that, because just to complete this, there are a number of processes where similar to the rapid steel or method from 3D Systems, but where the binders are much less binder content and much more compacting of the metals. X1 and Voxel Jet. There's just two companies that are making a lot of success. It's a bit like the ceramic printing I was mentioning yesterday. If you can predict and control the shrinkage during the furnace cycle, which is what they do, then you can come up with some really nice parts. In particular, X1, I've seen some excellent and very fine detail metal parts made using that. Much better than, say, direct metal printing, in fact. But the disadvantage is that they do shrink during the furnace cycle, and therefore, and you need a furnace cycle, so it's more expensive from that perspective. But it's definitely a route to go. So that's basically it. All right. I think that's actually the end of all of my presentations. So thank you very much for being a great class, etc. As I said, also really appreciate all of the discussions that we've had, both in the class and in the break times. I think you guys have obviously participated a lot in this, so that's excellent. Thank you, and good luck with all of your ventures in the future. Somebody had a question. Somebody raised their hand. Sorry, say again? That one? Yeah, okay. Do you just want to take a note of it? I was too quick? Okay, fair enough. So probably the particular point here is the third one about grain growth, and that's something that we're learning a lot more about. Essentially what you do get in a 3D printed pod is actually very regular microstructure compared to, say, conventional casting, where you don't have much control over the cooling rate spatially. So what you tend to get then is relatively small grain growth, which is synonymous with brittle and hardness. Ductility, although it says low ductility, most experiences is that it's not that bad, in fact. Probably you would only get, certainly if we compare it to castings again, so you can improve ductility obviously by heat treatment, and so that's the normal practice that you would use anyway, and 3D printed metal parts respond very well to heat treatment. Okay? Done? There was another question. Yes? Yeah. Well, I made this comment, I think, on the first day about how engineering researchers in particular should always have industrial context in mind, the application side of things. If you're more pure than that, even from the perspective, say, materials engineering or materials science, or science, then you can be a bit more fundamental. But I think that, so are you talking about academic career, or are you talking about a career path in general? Right, right. Yeah, well, I would say don't repeat my experience. The world changes, so you need to just understand a little bit about how different the world is today, or know about how the world is today. So that's one thing. So, yeah, I mean, how I did it would not be how you could do it now. Bless you. But in addition to that is also, that doesn't just mean societally or industrially, but also from the perspective of academically. Nowadays, you guys are under a lot more pressure than I ever was to perform. I was, I born into a time when academically what you did is you created your own pressure. So it's a lot different even from that perspective. My advice, if you want to sort of say, well, what's my main philosophical perspective, is you do the right thing. You always do what you think is the right thing to do. Don't strategize on what you think other people want. That's my advice to you and to everybody in this room. Do what you think is right. I mean, it may be that other people, they agree with that as well, so it's great. So have your own internal moral compass and go the direction that you want to go. And a friend of mine who's also a professor, he just retired recently, a couple of years ago, he used to talk about this wave effect in research. You do your work, and this is why I mean do what you think is right, because eventually the world will catch up with you, and there will be then this wave, and you will be in a position to ride that wave because you've done all the preliminary work when it's not been a cool idea. I mean, I always say I started 3D printing before it was cool. And that's kind of what I mean by that, is basically I realized that this was going to be a technology that will develop into what it is today and further at the outset. Now maybe, so I followed that, and I strictly, you look at my Google Scholar profile, you can see it as well. 5 publications, 5 citations, 10 citations, 20 citations, and then now last year, what was it, 6,000 citations. So it takes your time. So that's the wave. The wave hit me. I've been riding it, and I'm continued to ride it until it will die off and something else will happen. I mean, you look at other technologies around the world, for example, carbon nanotubes. When carbon nanotubes came out, everybody was doing research in carbon nanotubes. Yeah? And then what's happening now? You never see anything much on carbon nanotubes anymore because you've had graphene, and so now everybody's doing graphene. Same with electrospinning. Everybody was doing electrospinning. That's not the way to do it. You follow your guide, your compass. Go along that, and eventually it will happen, and it will be your time to take advantage of it. If you're constantly following trends, you've got no reputation. That's my philosophy. Okay? Anybody else? Ceramic implants. I mentioned a little bit about it. I don't have any real examples, and I've not really studied it very much. As I did once meet a guy called William Bonfield, who is a very famous professor from Oxford, who is credited with the first applications of hydroxyapatite when I was in Hong Kong. And even then he was talking about the possibility of doing things like stirrup bones and things like that for oral implants and things. I think that's probably where most of the interesting factor for direct, in this context of metals, and then putting that into the ceramic phase, that's, as I mentioned yesterday, the approach would be a binder-based method, and therefore you post-sinter to densify and strengthen the ceramic part to create an integral ceramic part. Those parts can be really good. A lot of detail, can be very small. You can, there's nanoparticle technology around that as well. And so it is possible to make really, really small auricular bones, for example. I think it's less appropriate for larger bones. because then you've got brittle fracture problems and stuff like that. I'm making that comparison to polymer ceramic matrix materials. That's different. That's using the ceramics in a very different way as a bioactive component. But where you want the strength of the ceramics themselves, I don't see that a lot of future in those, unless they're, for example, you know, you have a hip implant, and quite often you might have a ceramic ball. You might have a ceramic sleeve for a knee implant, and they could be made using 3D printing methods, perhaps. Coating methods might also be appropriate. Yeah, so that's pretty much all I can say about ceramic printing. Is it enough? It's enough, okay. Anybody else? All right. Oh, every time I think I've finished, somebody comes up with another question. Yes? I think there have been a few cases. I don't know specific cases. I believe I have read some papers where there have been direct production of ceramic implants, yes. Particularly. Yeah. Yeah, so I can't really comment because I've not really followed that area very much. I mean, yeah, I mean, the issue with ceramics is obviously brittle fracture. And you can't avoid that. And, you know, bones are, you know, I mean, okay. Mm-hmm.
Yeah, so right now we are working on polymer blend ceramics.
Mm.
Yeah,
Yeah.
here and there we have positives and negatives as well, but not much.
Yeah, I mean, obviously dental, there's a lot of ceramics, but that's a different story. And as I said before, yeah, polymer blends. The purpose of the ceramic is somewhat different. It's not as a structural component as such as it is there to help with bone growth and mineralization and those kinds of things. Okay? 5, 4, 3, 2, 1. We're done. So over to you, Ravi. Yeah.
So, just please raise the hand. How many people update for the Facebook? Just can you see maybe one side or can you spread across? No copying. And one more thing, if anybody wants to attempt, you can attempt. You can attempt. Even I am trying to attempt. Okay. So you can attempt the paper, but the people who opted for the paper, please get in.
Mm-hmm. Well, we talked about the machine learning side. You could actually do some machine learning on that. If you can sort of put some sensors in there which are directed at, say, surface temperature of the polymer as it comes out of the head, or directed at the head itself, and then you can get some feedback there. and then correspond that to sort of build geometries, so try different geometries and different parameter settings and see what happens, and sort of then use machine learning to tune it. That would be quite an interesting area to deal with. And I think there's people working on that, but there's not many, and I think it's definitely, you do it for that, and then you can maybe work out what other things I can do machine learning for as well. We're also considering how machine learning applies across multiple processes as well. For example, you might want to, in metal machine printing, you could print a hole rather than a machine a hole. So what would be your decision-making processes around that? And if you expand that to